Hi, kids! Hey, I'm gonna continue on with how a moving charge has a magnetic field, and if it's in a separate magnetic field, then it's gonna experience a force. So this was the formula that you had from before. Okay. So let's just talk about, well, this. We know a current-carrying wire has a magnetic field around it. We know a magnet has a magnetic field around it. When two magnetic fields interact, you get a force. Okay, but let's talk about what actually is current. Okay, current actually is, if you hopefully you remember, it's charge per time. So if I plug this in, I have B times charge per time times some length. Instead of saying length, I'm just going to call it, some random distance times sine theta. Hey, look. I'm going to end up with B times Q times D over T times sine theta. Oh, D over T, that's going to be velocity. So I don't have to have lots and lots of current. I could have just lots and lots of charge. I could have just a single charge, and as long as that single charge is moving, it's going to have a magnetic field around it. And then, hey, look, I got a magnetic field here, I got a magnetic field here. Two magnetic fields are going to give me a force. Okay? Hopefully that makes sense. The only thing you have to remember, so this is going to be how you find the magnitude. The only thing you have to remember when you're doing your second right-hand rule is that second right-hand rule, where before your thumb points the direction of the current, B was your separate magnetic field, palm was the force. Now your thumb points in the direction. Remember, what is current? Current's direction that positive charge goes. So you just have to remember your thumb points the direction that positive charge moves. So if you're talking about a negative charge, it's got to go the other way. So let me show you a couple of different examples. So just the only thing you have to remember is now your thumb velocity for a positive charge. So let me just do two examples, and then I'll show you a couple cool demos, and then that will be done with this one. But here, so let's say I have a magnetic field, like now, and then I have a positive charge that is going to move into it, okay? So if I wanted to find the direction of the force on this guy, I would go, hey, that's a positive charge. Thumb points this way. My magnetic field points in. That's this way. So the initial force would point that way. But as it goes into there, the force is going to change. It's always going to port towards the center. It's going to move in a circle. Yeah, a circle. Which means, in this case, centripetal force would equal this force. Hopefully you guys remember mv squared over r equals qvB. As long as it's 90 degrees, which it is, and you could solve stuff, and that's pretty cool. But does everybody see force, the velocity, magnetic field? So the initial force is this way. Later on, it's going to go like this, so it would be down this way. Later on, it's going to go like this. If it stays in the magnetic field, it's going to be this way. It's always towards the center. Centripetal force, which would be this. The only thing you just have to be careful about, so let's say I had a magnetic field pointing this way. That's my magnetic field. And I have a negative charge going this way. If I was going to set it up, I would have to set it up like these. So I'd go, oh, my thumb points that way because it's a negative charge. My magnetic field points out of the board, positive Z. So my force is in the positive Y direction. But again, as long as it stays in the magnetic field, you would still get that centripetal force from it. All right, I'll be back with a fun little demo. Bye, kids.